So I just wanted to, now that we have a couple more people on, look out for scikit-learn machine learning pipelines in 2 weeks, and then a month after, so a month from today, the first Thursday of the month, we're going to be diving deep into data science tips and tricks. The link is here. Right. So today I'm going to be covering time series analysis. So you're going to notice that I've shifted data sets from what I've used in the past if you've come to any of my classes. So I am going to talk a little bit about which data sets I am using. For one type of model, I am using the Missouri drug overdose counts to look at the trends over time in those. I wanted to also pull in some type of retail or data set that would have a lot of seasonality with it. And retail just in general does. So I got a Kaggle data set, the Rossmann store sales from online. The links to both of them are located here. The link to all the files is the bit.ly link in the chat right now. So what we're trying to measure in general are trends, patterns, and seasonality over time. We're obviously going to dig into that a lot more in a little bit. But the goal is really to understand both past, current trends, and then be able to forecast into the future. In my job, I've actually used time series more for understanding the past than for really understanding the future. I work in rewards and incentives, so it's definitely something that has come up quite frequently on the job with me. So I'll be interjecting with some information just from the field as well. So I'm going to be flipping back and forth between my deck and my code. So I'm going to start with an overview of time series modeling and what that is. So time series modeling, I found a definition that I really liked. Time series modeling is the endeavor of extracting meaningful summary and statistical information from points arranged in a chronological order. So what this really means is that we're looking at something over time, and we can't use the normal statistical methods because today's data point with time series is going to be highly correlated with yesterday's data point. For normal regression, regression assumes that observations are independent from one another. So you can't use that for time series analysis. Your models won't be valid. So we have to find and use different methods for time series than we do for normal statistical regression problems. And that's what we're going to be digging into today. Shown on my screen on the right are the Missouri drug overdoses, the overall trend for the data that we're going to be looking at first. And then we're going to be looking at the Rossmann store sale data set that is shown in red at the bottom. So those are just general trends. We're going to be digging into how to make those plots and just in time series in general. I'm going to be focusing more on the modeling than the code in general, though. So a couple time series use cases. How can you use this on the job? Something that I've seen when I worked at in the grocery area was forecasting future sales and transactions, just so they could understand when what their sales and transactions will look like, staff accordingly, and plan for that for inventory. We also used in that grocery company, we looked at time series and used it to understand the holiday effect of delivery sales. So that's another example. In the job, we've also looked at historical credit card application trends and the seasonality and events associated with them, specifically digging into rewards and incentives associated with those credit cards. So one of the things that we really like to do is look at the seasonality, the holiday effect, trends over time, and really try to pull out that random errors so we can understand how to communicate with our stakeholders. Is there a question? I think somebody's unmuted. Might want to mute if you're not talking. All right, thank you. So another type of thing that you can do with time series is anomaly detection. So a use case that we use this for recently is we have a lot of rewards programs for employee incentives at Merits where I work. And we wanted to understand misuse of rewards, or it wasn't necessarily fraud, but or people who don't understand the programs that they're participating with, or potential fraud, misuse. So that's another example. Another one that we're seeing a lot more on the field, especially when I worked in consulting, was predicting machinery and manufacturing malfunctions with the different like tools that they use on the job there. So often time series models run on IoT devices or Internet of Thing devices that are actually put into the machinery so that they can run those time series and make notifications if they suspect something is going wrong. So that would be a type of anomaly detection as well. Are there any questions about that before I move into more of the specifics of time series? Right? So now I'm going to be jumping into more of the characteristics of time series. There, for certain models, are a lot of assumptions. Think linear regression and logistic regression, and all of those assumptions that you have to go through before using those models. For some time series models, we have some similar assumptions that we have to look at before we can choose a model. So the first one that you always want to keep in mind with certain models, and this would be the classical statistical models that do time series. So ARIMA, moving average, autoregressive models, think those. So we have to look at stationarity. It's an assumption of some time series methods, and really all that it says is that it exhibits no trends or seasonality, and it shows a constant mean invariance. So you can see two different images here. One is showing data that is not stationary because you can see the peaks and valleys are getting bigger as you go up with the time series. So you couldn't use an ARIMA model on that data without transforming it. And then what it shows on the right is a stationary time series. You can see it looks a little bit more random. The peaks and the valleys look more similar. So it's not, we don't necessarily can't use a model that shows that it's not stationary, but we have to prep the data in a specific way to handle this type of data going into our models. So as I said, we have this stationarity requirement. So we have to find and make sure that our data has a constant mean invariance over time. So obviously most time series has seasonality, trends, and the things that make data not stationary. So similar to when you have to transform your data before going into a linear or logistic regression, you can do something very similar here. So the stationarity requirement can often be dealt with by first and second differencing, or even on to third, fourth, or fifth differencing. So really what that is taking the current time period minus the previous time period. It shifts your data up, and it actually does a difference between those two time periods. And if the first differencing doesn't work, you can actually go on to second, third, fourth differencing, which is really just taking it a step further and differencing using the results of the first differencing procedure. So taking, after we have differenced the data, doing that again and taking the current time period minus the previous time period. So after that, you can do some testing to see if it's stationary, and then you're able to possibly run AR, so autoregressive, moving average or MA models, ARMA or ARIMA models as well. And if there are, sometimes you can't make your data stationary, it happens. So there are other types of models that build in trend and seasonality, they build in how to deal with trends and seasonality. So we're going to show those types of models in the second part of the class. So now I'm going to flip over to my code. So as I said, there is a bit.ly link in the chat that has all of this code in here. So I'm going to start off and just kind of walk through the different things that I did to start off. I am not going over in this class just because it's way too much for one session. I'm not going to go through missing value imputation, a lot of the data prep going in. It's really, this is focusing more on the modeling side of things. I figured that that's the hardest thing to learn. So really wanted to just dig in as much as I could on the modeling aspects of things. So as we talked about, we're using the traditional time series first, and we're dealing with the Missouri drug overdose counts. So in general, I would have loved to have had overdose rates. That would have been much better for this use case, but apparently monthly overdose counts are, they're difficult to get. I couldn't find them anywhere. I could only find them broken down by county or region, things like that. So I just went with this data set, and I showed here, we have the data for time series generally has a month or a day or even a time of each day. So, and then it'll have the number of overdoses. So for this first part, we're going to use monthly data. For the second part of this class, we'll use daily data. So you can really start to see some of the differences between the two. So the first thing that I did here, often when you read in data without specifying data types, it will bring it in as the wrong data type. Remember, your data type always has to be a date time. No matter what programming language you work with, it's always that is a requirement. So here we're looking at our month. It is an object, so that's telling me that is not a date time type. This is already in the type that I need. The overdoses, they can be numeric or integers. So came down here. The next thing that I did is took and changed the pandas to make it a date time format, and putting it and specifying that it was in the month and year. So always make sure and check, just like I am here, to make sure that your date turned over and looked something like this, just to make sure that you did it right. And then I'm just subsetting my data to the month and the overdoses, because we're going to be going over univariate time series, which is time series with a specific or one value. The second model we're going to cover, you can add regressors, but you really need to move on to a different type of time series if you're really getting into like deep learning forecasting with a bunch of different factors. So that's not what we're covering today. So before I move on, any questions? I don't see anything in the chat, but I want to stop and see if anything you would want to talk about before we move on.
Hi, yes, am I coming through?
Mm-hmm. Yes.
I had a quick question about stationarity in terms of its visualization, slide 8. Would you say the emphasis is very important to the y-axis or no?
So there are actually, oh,
yes.
Sorry, go ahead.
No, sorry, go ahead.
There's a bunch of different ways to test stationarity. So we're actually going to go through that in the next couple of slides. So we're going to do it from a visualization perspective as well as a mathematical perspective. So those are going to be the next things we dig into. And then I think it'll become really clear with your question once we dig into that, because it's really talking about how the trends lead to stationarity or not.
Okay,
so.
Thank you.
Mm-hmm. Any other questions? So the next thing that I'm doing, it's a little bit different when you're doing forecasting in time series. Normally in machine learning, you would randomly choose certain values to put in your training and test data set. But when you use this in the field, you're really going to be looking forward. You're not shuffling old data. So you tend to do the training and validation data sets You'll take a certain time period, make it your training data, cut it off, and have a certain set of dates for the validation data set. Based on the size of my data, it's not a very big data set. I went through and just split that based on the size. So the first 66 observations are in my training data set. And if we look, the overdoses.shape, so actually we want to do overdoses temp. It tells me that I have 78 data points in this particular data set. You'd usually want more than that, but this is more for demonstration purposes. The more time, the better, especially with time series. It's ideal to have 2 years so you can really see more of that seasonality, but this is what we were working with here. Wanted to have a simple example for you guys. So the first 66 observations are my training data set in this case, and the rest are put into my validation so I can test how my model is doing. Like I said, in the real world, you'd want more than that. But for today's purposes, it works just fine. So now we come down and we see, and I think this might start to answer your question. We plot this over time. The first, I don't even have to test anything, and I know this is data is not stationary. Like I don't even need to look or do anything. So as is, this data would not be usable in this specific type of time series model because you see this trend over time. We also might be seeing somewhat of a seasonality as well. That is a little bit more like squishy because it may just be the trend is changing. So, but we are definitely seeing that there is a change in trend. So what that tells me, okay, clearly it's not stationary. But for demonstration purposes, I want to go through the next visualizations to show you what non-stationary data looks like and how we would catch that if the visual wasn't clear. So I'm going to move back to my slides. So one way that we test for this is actually a mathematical way. I'm not going to get deep into the math of it just because we don't have a lot of time. But one way you can think of it as when you're doing a t-test, you test assumptions with different statistical tests. This is similar. We run a Dickey-Fuller test, and this tests an auto-regressive model, which is usually what you're using when you're testing for stationarity. And it tests multiple lag values. So I'm actually going to skip forward just so we can talk about what a lag is, and then I'll come back to the Dickey-Fuller test. So we talked a little bit at the beginning already about autocorrelation. I didn't call it autocorrelation, but it's something that is almost always involved with time series data. So the autocorrelation is really simply just the correlation between two data points at different points in your time series. So an autocorrelation is also measured in lags. So if we had a lag of 1, so if I was looking at time series of like the current period that we're living, if I compared today to yesterday, that would be a lag of 1. If I compared today to 2 days ago, that would be a lag of 2. And it looks at the correlation between those two values back into time. So that's what a lag is called. So those two examples hopefully make that that clear. But in order to look at these lags, we look at autocorrelation plots. And we are able to see how correlated today's data is with yesterday's and the day before yesterday, so on and so forth back in time. So we can also uncover stationarity, seasonality, and trends in these plots as well, just visually without that mathematical test. So looking at this data here, so this is an example of an autocorrelation plot. You can see here, and I'm going to zoom in a little bit. These red lines are telling me that they are statistical significance lines. So anything that is above these red lines tells me there's statistically significant autocorrelation happening. So you can see this here, that we have statistically significant autocorrelation with yesterday or lag 1. And then we also see statistically significant autocorrelation with a lag of 2, so 2 days ago. So looking back 2 days in time. And then it goes forward all the way up, in this case, like lag 28. And you can see that after the first 2 lags here, the autocorrelation is no longer statistically significant. This data shown here is stationary. In general, when you see this steeper drop off under this red line in the first couple of lags, and then you see more of a random pattern into the future, that's a pretty good sign that your data is stationary. So if I did the Dickey-Fuller test on this right now, it would tell me that almost certainly my data is stationary. So what does non-stationary data look like? Zooming in quickly. And if we look here, we are seeing different autocorrelation plots. So this first one is random. So you're seeing that there is really no pattern going on here. Today's data is not correlated with yesterday's data at all. So what this tells us is we actually don't want to use a time series in this case. Regression is fine because our data points are independent of one another. So we would go use linear regression in this case. What you're seeing here, the trend, we can see in general that these autocorrelation has a very specific downward trend. That is not stationary. If you see something like this, you can be sure that that data is not stationary. And this general pattern, in general, this is what you're going to see when you see a trend. I have an example in my slides. And this is showing a seasonality. So you can see the bumps, ups and downs, the cyclical cycle of this. This consistently oscillating over time, that shows that our data has seasonality and that it is also not stationary. Seasonal data breaks those assumptions. So before I move on to the autocorrelation plots and dig into it in detail, so let's come back in here. So we see clearly this overdose data has a trend. So based on what I just told you, I'm looking at the autocorrelation plot here, and it shows exactly what we said. That we see this consistent downward trend telling us that our data is not stationary. So that's generally what you see. I'm going to come down quickly to this particular data set. This is the first difference data set. This is stationary because we have a quick drop off here after the third lag for the most part throughout, with a couple of exceptions. Our lags are not statistically significant. So once you see the Dickey-Fuller test down below, it will tell you that this data is it's stationary and we're good to go. I did want to show a couple of examples there. And this right here is the first difference data. So
hey, Kelsey.
Really, go ahead.
The second plot you showed that was stationary, what about the fact that it goes down below and then starts to regress towards the mean? Is that a concern?
Yes. So because this doesn't have a consistent oscillating pattern, we're okay, and that it's mostly within those bands. There is an autocorrelation plot down here that shows seasonality, so you can see the difference. I'm just going to scroll down, hopefully. You see here, this is showing seasonality. This is our retail data. So you can see here that it drops, but it's a repeated up and down, whereas the other one just kind of goes down and then it goes up. So, and almost all of these are above the statistical significance line, and you can even see the same peaks and valleys at the bottom too. So this is more what seasonal data looks like. Does that help?
Yeah, that helps.
Awesome. Try to find very varied data so you guys could see it. So coming back to this real quick, these are really kind of perfect examples. Like we just showed there, it's often more nuanced than that. So that's why we actually look at two different ways of looking at it. So we not only look at autocorrelation plots, we also do the mathematical statistical test because they're not always going to be consistent. But if you have two things telling you they're not stationary, you can be pretty confident that you need to transform your data. So there's also something that we use in general are called partial correlation plots, or this should be actual partial auto correlation plots. So this is a very similar thing to what we've seen in the past graph with one change. So it's similar, it's showing autocorrelation, but it only shows the correlation between each point that isn't already accounted for in the prior points. So you can think of it almost as like when linear regression, when you're controlling for something. Well, you can see this graph looks quite a bit different. So we have those lags, but we have here the correlation between today's and yesterday's date. This is very high, and it's almost actually, if you see here, it's almost a perfect correlation between today and yesterday. And then between today and 2 days before, we almost see a perfect correlation. So it's actually also, when say you look at lag 3, it's only looking at the correlation that is not already explained by lag 1 and lag 2. This isn't really helping you as much with stationarity, but it's going to come in on choosing our model in just a minute. So these partial autocorrelation plots will come in there. So we looked at partial autocorrelation plots. I'm going to go into why we care about those, and then I'm going to come back to the code and start going through a little bit more of it with you. So there are different types of models. So the first, I would say, component or type of model that you can use is an autoregressive model. An autoregressive model is a linear regression model that uses its own lagged values or its previous values as its predictors. So in linear regression, you use a lot of different, like if you wanted to do a regression on state overdose rates, each state would be a data point in your regression. Here, instead, it's the previous values that are our predictors for this time series. So in general, when you see this, you're going to see AR1 or AR2. All that's really telling you is when I'm doing my autoregressive model, AR1 means it's a regression between today and yesterday. AR2 is between today, yesterday, and the day before that. So yesterday and the day before are our predictors. So you can see here an example of an AR1 and an AR2. As you might expect, when we're using just yesterday for our prediction, we have a really noisy data because there's really going to be a lot of variation. You're only looking at 2 data points. If you go to AR2, it becomes a little bit more smoothed out because we have at least another data point as our predictor. So that's what an autoregressive model is, and that's one option for certain types of data for actually modeling. It's also a component to ARIMA models. You've probably heard that before. If you've read anything about time series, ARIMA is extremely common. So this is the AR in ARIMA. Are there any questions about this? I'm going to go into how we know which one to use in a minute. So now I want to show just in general how we would use the partial autocorrelation plots and the autocorrelation plots to know if we wanted to use an AR component, so an AR model or an ARIMA model. So in order to look at that, we actually not only need to know whether we're going to use it or not, we have to figure out how to put it in our model. So if we're choosing if we want to have a component in our model, and I'm going to come back here really quickly to our ARIMA model. This 2 is our AR order or our AR component. So that's what we're talking about right now. We also remember the differencing. This is our differencing component. And then there's a third one that we're going to go over that is MA or moving average. And this is our moving average component. So and this is all within an ARIMA model. So you can say AR is autoregressive. I don't know what it stands for, but it stands for the differencing, whether you difference it or not. And then MA is moving average. So you're starting to see it come together and why I'm talking about this. So sometimes you want to use just a moving average model. Sometimes you just want to use an AR model. And sometimes you want to use both of those, or maybe even differencing as well. But you have to do some investigation before you can see which one you want to use. So shown here is a partial autocorrelation plot. So this is why we need to use this. So we can choose an our AR order looking at this plot. So they think the 2, 2, 1 that we just saw, it was the first 2. So you can see here that in this case, we have a sharp drop off of our partial correlation plot. We want to choose our AR order, and that's really looking at coming back to the autoregressive. It's in our ARIMA model, how many time periods do we want to consider as predictors in our ARIMA model? So how far back do we want to go? What the partial autocorrelation plots show you is how far back do we want to go? In this case, you want to look at when the partial autocorrelation plot becomes not significant. So in this blue value here. So you can see here that this one's pretty obvious. We want to use AR order of 2, meaning our predictors are yesterday and the day before. So it goes back 2 time periods for our forecasting. Because it drops off to 0 basically after that second one. So the partial autocorrelation plot helps us identify AR or our autoregressive part of our model. Now we've talked ARIMA, so there's the MA component as well. So a moving average. So it is similar to an AR model, except it has a little bit of a twist on it. It makes a prediction, and the linear regression model is actually on the forecast errors or residuals, if you've ever heard that term. So it's actually using the error values in our prediction as the predictor for our forecasting. It really returns a weighted moving average. And it again, we have to tell it how far back to go. Do we want to go back 1 time period? Do we want to go back 2 time periods? So you can see this looks kind of the opposite of the AR models. The first one here is not as noisy in MA of like going back 1 time period, and the MA2 is more noisy because now it's really switching to error. So now that we're looking at error values, looking back 2 has the error component of 2 data points. So it looks even more noisy. So you're probably starting to understand why you might want to use both. They both do 2 different things. And when you take both into account with an ARIMA model, you can get a better model than each one of them individually in most cases. So in this particular case, this is where we move back to the autocorrelation plot. So remember, partial autocorrelation is what the lag actually controls for the correlation that has already occurred. So a lag of 3 in a partial correlation plot is the correlation not explained by 1 and 2 lags. Now we're moving back to autocorrelation plots. And so this is just, is today correlated with yesterday? And is that correlated to the day before? So that's where we're moving now. You can think of partial autocorrelation, autoregressive, or AR. Autocorrelation, moving average. So here it works just the same. So here I see that the first two lags, the first lag, after we see it, it drops off to close to being statistically, not statistically significant. You could, in this case, you could try a lag of 1 and you could try a lag of 2. And you would probably look at the errors or the mean squared error to see which one is better to do. So this tells you when you see this drop off that we need a moving average component. So how do we know which one to use? So this is something that if you're doing these models and testing them, you kind of want to have it on your second screen, because this is hard to kind of conceptualize sometimes. So I put a pretty, hopefully easy to understand table up here and then the visuals associated with it. So if we see a gradual downtick, and I'm gonna scroll up, scroll in. So if we see a gradual in the autocorrelation plots shown here, and we see a steep drop off in the partial correlation plots, that tells us we want an AR component only. If we see a steep drop off in the MA, that's shown here, and then we see a gradual, a steep drop off in the autocorrelation here, and we see a gradual downtick in the partial autocorrelation, that tells us we want MA only or moving average only. And seeing a gradual in both cases, it's more gradual, even if it's like bouncing from positive to negative, you can see it's more gradual on both sides. That's when we want to move on to an ARMA or ARIMA model where we use both the moving average and the autoregressive components. So I'm going to come back to my code so we can actually see it in action. And I tried to go through and annotate. I might not go through all of these, but tried to annotate the process and what I did. So here, coming back to where we were, this is a trend. It's not stationary. We can pretty much move on at this point. I did show the partial autocorrelation plot just so if it was stationary, in this particular case, we're seeing that this had a gradual decrease and this had a steep decrease. So you would just use an autoregressive model and not an MA or moving average model. It's not stationary, so that's just a hypothetical, just so you can help it to understand. So coming back to the Dickey-Fuller test, it actually looks at previous lags and looks at the correlation between those lags. I'm not going to get too far into it, but if you run a Dickey-Fuller test, as shown here, you want to look at the statistical significance value. If you see the p-value is above 0.05, if you're using like a traditional cutoff, that tells us our data is not stationary. So going to come back in here, come back to the Dickey-Fuller. So it looks and runs an autoregressive model, looks at the different lags. The null hypothesis is the data set is not stationary. So if you get below a 0.05, that tells you that you can reject your null hypothesis and you can consider the data that the data is stationary. So you saw just on my code one that was not stationary. You can see now this p-value is way below 0.05. So this is an example later on in the code of when it was stationary. So coming back to here, we see the p-value above 0.05, which double confirms that this is not stationary. We pretty much already knew that. I know I just covered a lot of ground, so I want to stop, even if we can only go over ARIMA and have to push profit models into the next class. I think it's a lot of material. Are there any questions? All right. So now we're going to go through more of the process of what it would look like. So clearly, first, the data as is, not stationary. It's not going to work. We can't put it in a model. So we come down here and we do our first differencing. So in this case, we are just taking the overdose rate of today in each case, and we're doing this for each data point, and we're subtracting the overdose rate from yesterday. You can see that I have put a dot shift, so it's shifting it one down and then using that to difference from today's date. And then I'm doing that for my test set as well, just so I can be able to put that in the model later on when I'm testing the error values. And then when you do that, and if you don't drop the null values, and I'm just going to real quickly show this. First difference. So here you can see we, in this case, had almost a perfect correlation, you remember, and then it actually shifts your data down. So you can see you have a missing value here, which is why you see the drop NAs for my pandas data set here. So when I drop the NA, it looks down here and it's basically shifted my data and found a difference. And then my first differencing plot looks here. So this looks like it could be promising. It looks like it might be stationary. There's not really a trend going on here. The peaks and valleys are pretty random. So not sure yet, but it's looking pretty promising. So coming down to here, we see that there's a pretty steep drop off, and for the most part, it's staying within the bounds of the statistical significance in our autocorrelation plot. We're also seeing that there's a gradual decrease for each lag in general, which tells us that a moving average component will be necessary if we use this first difference data. Now, when we come down to the plot of the partial autocorrelation, we see again that gradual decrease, which tells us that not only is a moving average component needed, an AR component is needed as well. So here it hits statistical, it's not statistically significant at lag 4. So we want to use a moving average component or parameter of 3. Down here, we see that it's not statistically significant at lag 2. So our AR component or order would be 2 in this case. Now we move on and test mathematically as well what we just tested with our plots to see if our data is stationary. It's below a p-value of 0.05, which tells us our data is definitely stationary. We've confirmed both visually and mathematically, we can be pretty confident in that. So you'll see down a little bit farther in the code, we actually use this data and try it in a forecast. So I still went through the additional steps that you would go through, assuming that wasn't stationary. What would I do next? So the next one, I actually went and found the second difference data. I also did the third, fourth, and fifth, and sixth to just see what it would look like, which you're welcome to do. All you have to do is change this, and it'll move it to third difference or fourth difference, but this is second difference data. So we're seeing here, there's less noise still, and it's more random. There's really no trend going on in general, except for maybe a couple of outliers here. So looking at our autocorrelation plot, it's kind of on the borderline. I'm not really sure if there's a trend going on here. It could be stationary, it could be not. It's a little bit like, this is when I want to say, okay, I kind of want to see the statistical test too, to confirm one way or the other. It's kind of in the middle. But again, we see that gradual decrease in the autocorrelation plot. So we want a moving average component. It's a moving average component of 3 because these 3 are statistically significant. Then moving on to the partial autocorrelation. This is looking pretty random, mostly statistically insignificant, but we're again seeing that gradual decrease, which tells us we need an AR component as well. In this case, it would either be 4 or 5. This would be a gut call. You could do 4 or 5 or 6. Probably 5 or 6 would be our best bet. Looking at that, and we're actually going to graph this one too, or model this one too. So, and then we come down, do our Dickey-Fuller test, the p-value below 0.05. So it is, the graphs were kind of borderline, but the math pretty much tells us it's almost certainly not. It's stationary, we're good to go. So say differencing hadn't worked. It did, but what would we have done next in that case? We would have probably gone on to log transform the data and even do a differencing of that log transform data. In this case, the log transform data had a trend, not stationary, which you can see clearly in our autocorrelation plot, so we couldn't use this data. Transforming it wouldn't have worked. So come down to our Dickey-Fuller test, confirm what we saw from our eye. It's not stationary above 0.05. You could also find the square root, and I found this 5th different square root here, just because I went and I tried 1, 2, 3, 4, 5, none of them worked. Or I think it was 5 was the first one that worked. So we're seeing here, this again is kind of in the middle. We're seeing some trends here. It may or may not be, but it doesn't look like it's close enough together to be seasonality. So I'm not sure. Go on here, still the autocorrelation. We're seeing, I'm kind of in the middle, not sure if this is stationary or not. This could be a trend. And we have the partial autocorrelation. But we come down here, it is statistically significant. So that means it is stationary. The reason why I was kind of at I don't know, but you're seeing how long this data is. So it's really not doing a monthly pattern at all, because like 2016 is between here and here. And it's kind of oscillating and going back to normal over the years. So that's why it's stationary in this particular case. If you put like a trend line in here, it would pretty much not have a trend. So we could have used that as well. So what I ended up going with is the first difference and second difference data, and I ran an ARIMA on it. So remember above, so when we looked at the first difference data, I'm going to come up and see where the 2 and the 1 came from. So coming back up to what we already looked at. So this one is the first difference data. So here, the autocorrelation plot goes with the moving average component. So this one, I think the first difference data was my second model. But we're looking at the moving average component would be about 3 in this case for our first difference data, and it would be 2 in this case. So come down. So this is our second difference data. So I did that out of order. Sorry about that. So this one is showing what we saw above. So we have our, I believe it's the AR is first. The differencing, we're telling it's first difference, and then our moving average component is third. So this was our first difference data that we put through. The reason I put it second is because it ended up being the better model, so I could go on. But we come down here and we are able to look at these p-values as well to also do another check that we chose the right thing. So we can see the AR of 2 or order 2 is statistically significant, so we're good there. The moving average component of 3, statistically significant, we're good there. We're good. We can do it. Our model is valid with our assumptions here. Our results, we look at the error values or the residuals. So you want to see somewhat of a bell curve here. The higher up it is, the hump is around 0. So getting pretty close with our error values for the most part. We can then, just like other models, do a validation. So in this case, we use our test and validation data set. This model is horrible. So our first stab at this is showing that this model just is, oh, that's the first model. So coming down to model 2, this one is a little bit better. Sorry. So we had the first and second model. I just show you the first difference model. So that's what we're showing here. It's looking pretty good, whereas this one is absolutely terrible. And then we see here the mean squared error, 1850, and MAE of 39. The first question I always get is, what is a good mean squared error? What is a good mean absolute error? There is no good MAE or MSE. You can only compare models from one to the other. So now I'm going to come up and show you my second difference data. So here, we see the second difference. I'm going to come up to my second difference data right here. So again, we're seeing here for our moving average component, it's between 2 and 3 that we want to use in this case for our moving average. Am I looking at the right model? Yes. So the second difference data, and then we can see that 3 here as well. So for our, it's between 3 and 4 for our partial autocorrelation plot. So looking at our second model is down here. So this is our second difference data. I actually think I made a mistake here. This was incorrect, which is probably why. So we're not seeing statistically significant here. So that's how you catch an error, guys. We see that those were not the right parameters. So I actually should have done that a little bit differently. So that is probably why we are seeing an absolutely terrible, horrible model here when we're looking at our predictions. And if I would see those p-values, I would say this really isn't a model worth running anyway. We can see our MAE and MSE are much, much bigger than down here, which tells us this is our better model. Now, is this a good model? Not really. ARIMA in general, most data does better with a seasonality model. And that's what I was going to get into, but this is a somewhat complicated. I underestimated how much time this would take. So really, that was going through this was my presentation on ARIMA. One thing I do want to touch on is seasonality and trends. So what if your data is you can't get it to be stationary? That happens. I actually tried a couple data sets before I could find one that I could actually get stationary. So there is a form of ARIMA that controls for seasonality, but not trends. You can't use ARIMA at all if it's trends. And if you have seasonality and trend, that's where you move on to something that has a seasonal component and it has that trend component, which Facebook profit models is what I often end up using on the job. I don't do a lot of forecasting, but I like to go back and understand past patterns. So that's what I would use, or something that has a seasonality and trend component. But we're unfortunately at time. I'm going to stop. There are 3 minutes left. I'll schedule a Facebook profits class. Maybe I want to do the pipelines 1 and 2 weeks. Maybe we can push forward the class schedule so we can cover profit models. So I think it's pretty interesting. Are there any questions?
Hi, can you clarify what you mean by steep and gradual when we're looking at the autocorrelation and partial correlation plots?
Yes, absolutely. So that's actually why I actually loved this visual here, because it was because I actually struggled with this too and explaining it. I look at a lot of websites and to help explain these things to you guys as well. But here is an example of gradual And this is an example of gradual as well, but in a very different way. So these are examples of not gradual. So you can see after 1, it goes down to nothing. And this one's after 2, it goes down to insignificant. Whereas these, it's more of a stair-step effect. So that's what I would say. And then these two are both gradual. So you would want an AR and an MA component here. And in general, with modeling, it's always like throwing something at the wall and seeing if it sticks. It's like that for time series too. Often, if it's kind of in the middle, you probably want to test both ways. So that's something to always keep in mind. We had those p-values, so I was able to see when I was wrong. So you're able to do multiple checks on yourself if something isn't really clear cut. Any other questions?
That was helpful.
Any other questions? Love questions. All right, so I am going to do oh, sorry, was there a question?
Do you have any book recommendations for people that are starting to learn about data science? I came here just to be a spectator.
Mm-hmm.
I'm trying to self-teach myself Python. So yeah, just asking if you have any, at least for time series modeling, if you have any recommendations.
So for time series modeling, I actually I read a lot when I get ready for these classes, and I found a lot of links that I really liked. So I just threw them in the last 2 slides just because it covers everything that I covered in more detail than I covered it. I also really like this book here as well. And then this is basically everything I used on my slides. I also, in general, show my website. It's kelseymnet.com. I have under information and resources. If you go down to, this has websites, and it not only has, it is broken out by model. So there's a lot more than just time series in there, but you can see time series, general principles, moving average, ARIMA, whole winter, it goes on and on and on. So every time I study something, I stick it in here. You can also find more resources in useful books. So for the most part, I've read these. So I believe time series is towards the bottom, the practical time series. There's actually a link to it that you can go to. So in general, and when I put up my video, I'll have suggested reading at the bottom of my classes. So you can see if you go into my machine learning class, let's just choose lasso and ridge regression. You can see I have suggested reading at the bottom of each page once my videos are posted.